Well, welcome back, 8th grade students. In the last video in this lesson, we got done talking about the rate of change. So I just want to real quickly recap rate of change. We saw that the rate of change describes the amount that the dependent variable changes compared with the independent, and we kind of broke that down into y over x, y compared to x. At the very end of our lesson, we saw that as they walk faster and the rate of change increases, then the steepness of the graph increases. If they walk slower, the rate of change decreases and the steepness of the graph will also decrease. In this lesson, we're going to learn about the slope of a line. So the graph shown represents the relationship between the time Jack and Jill walk and the distance they walk from home, just like in the last lesson. We're going to analyze 3 different moments in time during this walk to the bus stop. So when t equals 1, when t equals 3, and when t equals 6. The graph is already showing a right triangle that represents t equals 1. So we're going to trace that on a piece of patty paper. So if you have your patty paper, we're going to trace it on patty paper, and we're going to label the horizontal and vertical sides with their lengths. So I'm going to put this right on my graph, and I'm going to trace this triangle here. This bottom side, the base here, is a distance of 1. And if I look, the height is a distance of 1 1/3, or 4/3. Now draw right triangles to model t equals 3 and t equals 6 on the coordinate plane. So let's do that first. So t equals 3 is right here. So this second point on the graph represents t equals 3. So here's the right triangle that would represent t equals 3. And then t equals 6 would be down here. So this point. So I'm going to draw a right triangle straight up this vertical line. Down here's the base. And my line is the hypotenuse of it. Then it says trace each triangle on a separate piece of patty paper. So I have my patty paper for when t equals 1. I'm even going to label it. This is t equals 1. So now I'm going to do the same thing for the t equals 3 triangle. Trace it. And I will also label the horizontal and vertical sides here. So down here, this is 3. Up, the height goes up to 4. So this is 4 for the height, 3 for the base. Get another piece of patty paper. That's when t equals 3. This one is going to be when t equals 6. So all the way up this line. Probably would not be a bad idea to have a straight edge as you do this. So you can make these nice and straight. And then let's label the horizontal side as 6, and the vertical side is 8. And again, that's when t equals 6. All right, so we've done that. Now it says to determine the steepness of each triangle by writing a ratio of the vertical side length to the horizontal side length. So let's start with t equals 1 here. So when t equals 1, my ratio would be vertical side 4/3 compared to the horizontal side, which is 1. So my ratio would be 4/3 to 1. For when t equals 3, my ratio would be 4 to 3. And when t equals 6, my ratio is 8 to 6. It also asks, how do these ratios compare? At least for these two, it's fairly obvious. This one, maybe not as obvious, but these ratios are all equivalent. If we were to simplify them down, or if we were to find the unit rate, we would find that all of them were the same. So the ratios are equivalent. Number 4, so we're jumping over to page M2-29 now. What is the relationship among the 3 right triangles? So if we look at these 3 right triangles that we have on our patty paper, the first thing I notice is that they are the same shape, but they are different sizes. So the relationship among the 3 right triangles is that they're similar. The 3 triangles are similar. Question 5. Identify and label the triangle that represents the unit rate. So now we're looking for unit rate. Unit rate, we've learned, means it has a denominator of 1, or where the independent variable or quantity is 1. So the only one that has that is our original triangle when t was equal to 1. So the unit rate is 4/3. We're talking about yards per second, per 1 second. This is the triangle for t equals 1. And we know that because unit rate means denominator has to be 1. We know this because the independent quantity is 1 unit. All right, good. Slide the unit rate triangle along the graph of the line. So now I'm going to take my unit rate triangle and I'm just going to slide it across. And I'm looking to see if I notice anything. So it looks like that unit rate triangle is the same no matter where. So that unit rate triangle kind of fits the line no matter where I slide it, right? So between any 2 points, it connects any 2 points on this line. So let me type this here. So the unit rate triangle, I notice it connects any 2 points. You could also say the unit rate triangle fits anywhere on the line. As I slid it, I just noticed that it kind of fit. No matter where I put it, it fit. slide the other two triangles. So let's get rid of our unit rate one. Let's try t equals 3. We know it fits there. If we just slide it up a little more, still looks like it fits, right? If I go from this point to this point, it fits, it connects them, right? So I'm noticing the same thing here with the triangle for t equals 3. Let's see t equals 6. Obviously, it's the biggest one, but even if I just slide it down the line, that hypotenuse stays right on the line, right? So I'm noticing the same thing with the other two triangles. So let's put that in there. I notice same thing with the other two triangles. The other two triangles also connect any 2 points on the line. So interesting here that all of them connect the same things, and this is where this is going to lead us into slope. So in the last two activities, we've investigated a relationship using rate of change of 4/3 to represent Jack and Jill walking 4 yards from their home in 3 seconds, or as a unit rate, 4/3 yards per second. Because this situation is a proportional relationship, the rate of change can specifically be called the constant of proportionality, represented by K. In this activity, you created 3 similar triangles, each using 2 points from the line to explore the steepness of the line. By sliding the similar triangles along the line, you notice the steepness of the line remained constant between any 2 points on the line. That's what we just got done answering. We could slide those triangles. The hypotenuse of those triangles stayed the same and fit right on our line no matter where we were. In any linear relationship, slope describes the direction and steepness of a line and is usually represented by the variable m. I would like for you to highlight or underline that. That is what slope is. It describes the direction and steepness. Slope is another name for rate of change. So now we've seen rate of change is connected to constant of proportionality, and now we're connecting that to slope. All those things mean the same thing. It represents the ratio of the change in vertical distance to the change in horizontal distance between any 2 points on the line. That's another sentence I would like for you to underline or highlight. Slope represents the ratio of the change in vertical distance to the change in horizontal distance. And it also tells us that the slope of a line is constant between any 2 points. So I want to just summarize slope here real quick. They said you use the variable m, and it said it is a ratio of vertical change to horizontal change. Vertical change compared to horizontal change. That's slope. And then it also tells us that the sign of the slope indicates the direction. So positive, the graph or the slope, the line is going to go up from left to right. If it's negative, it's going to go down from left to right. So it said it gives us the steepness and the direction. The direction is indicated by the sign, positive or negative. Steepness is the ratio. So we wrote this equation earlier, d equals 4/3 t to represent the distance d Jack and Jill walked from home with respect to time t. Now we're going to generalize that. They're saying let y represent the dependent variable, the same as d, x represent the independent variable, the same as t, and m represents the slope, which in this case was the 4/3. Write a general equation to relate these quantities. So I'm just replacing all these things with different variables. Y is the dependent one, so in place of d, it's y equals. We're using m to represent the 4/3, and then x is the dependent one in place of t. So here is a general equation that relates those quantities. let y represent the dependent variable, x represent independent, m represent slope. That's what we just got done doing with that equation. How is this equation similar to the equation for the constant of proportionality? So if you remember, the constant of proportionality was a ratio of y over x. Well, if we have this equation, y equals mx, and I solve it for m, that means I would have to get rid of the x that's being multiplied by m by dividing by x on both sides. And these would just cancel each other out. And I'd get m by itself. And look at that. It's the same thing as the constant of proportionality. So m is equal to the change in y over the change in x, just like the constant of proportionality was the ratio of y's to x's. So that wraps up this activity. We learned once again that slope describes direction and steepness, and it is a ratio of vertical change to horizontal change. Have a great day, everyone.